And we continue the afternoon session with a talk by Alessandro, and he will tell us what the title is, Understanding IDS3 Successes and Challenges. Please.
Thank you very much, Fiona, and thank to all of the organizers for the opportunity to present my work here. And in fact, I decided to take the opportunity to give a little bit of a review of a lot of activity that has been going on in studying ADS3-CFT2. So this will be a bit of a review talk of the last several years of progress, and I will skip over some of the technical parts, and I will also skip over some exciting developments. For instance, there has been a very interesting work on the Virasoro-Shapiro amplitude in this context, and I think Shai will be telling us about, but I will not discuss it in this talk. And there has also been talk about deformations of this model, or the work about this, but I will not discuss it in this talk. I will stick to the simplest setup. So this will be a review of the work of several people, but at least recently I've been working on this with Davide Polvara, who is sitting there, and Sergei Frolov, who was here last week, but is back in Dublin teaching. So let me talk about ADS3 backgrounds, and I picked the most supersymmetric ones, not the formations. So there's always ADS3 cross S3 cross something else, and you can have T4, K3, or S3 cross S1. And they all have the same amount of supersymmetry, but they are a little bit different, these three families. They are all dual to some sort of n equal 4,4 two-dimensional superconformal field theory, and largely we don't know what these theories are. For the purpose of this talk, I will focus on the first one, the one with the T4, which is by far the best understood. Not only that, I will actually focus on just the problem of computing the spectrum of planar strings on this background. So I will pick what was also, in the case of ADS5 process 5, the biggest first achievement of integrability. And in fact, this is a family of backgrounds, so let me tell you a little bit about them. First of all, the symmetries, we all love a good symmetry. So ADS3 has isometries which are given by SO2, 2, and this you can split into two copies of essentially SL2R. And I will always denote the generators as something for one copy and something with a tilde for the other copy. Bold letters are my generator for my operator. And similarly, SO4 splits into SU2s, and I will call J the SU2s as opposed to the SL2, which is L. There are also supercharges, come back later. But what we're interested in for this time is just the thing that we want to compute the spectrum of. So we want the spectrum of the energy, and the generator is L0 plus L0 tilde. Okay, so this is time, the one that corresponds to time in ADS3. And this is not quantized, whereas all the other combinations, for instance, the difference of these two guys and the various J's from the S3, they're all quantized. In fact, as he built it, it's convenient to consider some combination of E and J, in particular here, the total E, so L0 plus L0 tilde, minus the total J, J plus J tilde. Okay, so this is what is convenient in this model, and this, I will call it H as in Hamiltonian for reasons that will become clear in a moment. Okay, I told you it was a family of backgrounds. So what are these backgrounds? The simplest one comes from a system of MS5 branes and fundamental strings, lots and lots of strings, and K branes. And then what you find is that these are backgrounds that have a B field, and they can be described in terms of essentially a single parameter in the simplest setup, which is the tension of the string is proportional to K in units where the radius of ADS and the sphere are 1. Supersymmetry forces these two radii to be the same. And the action is that of a Vesumino-Witten model, with the part which is an Vesumino-Witten model for SL2 and the part which is for SU2. So this was known since a very long time, and also the solution of the spectrum for this model is known since a very long time, but I want to very briefly review it. So as I said, you take the string background or superstring background, you study it in the RMS formalism, and what you get is some Kac-Moody of SL2 and of SU2, and the levels are shifted a little bit. That's a technical fact, is because you want to decouple some fermions in the RMS formalism. So in the end, you have this plus free fermions and also some free bosons from the T4 part. And you just have to figure out how to construct a theory from the representation of this Moody algebra, which has the right physical properties. And the simplest idea is that you take some reference state in the simplest setup with some highest weight state of this Moody, and you act on this sort of fiducial vacuum with a bunch of oscillators, exactly as you would do for flat space, where you act with some alpha minus n, the creation modes of the string. Here, the creation modes are some similar things which involve all the various modes of this field. So they involve modes of the currents of the Moody, they involve the free bosons, the free fermions, all of it. And everything comes into two copies, one with tildes, one without tildes, because there is a chiral split of this worksheet CFD. The full story is a little bit more complicated than that, but by and large, this is the idea by which you get the spectrum. You still have to impose the Virasoro condition. The Virasoro condition tells you that there must be some relation between all these various numbers. And in fact, the only number which is not quantized, n is quantized, the various R charges are quantized, is this L0, the SL2 charge of the fiducial vacuum. And basically, you've got to solve for that, and you get a solution which looks like this. So this would be the energy of a physical state in this story. And you see that it looks a little bit similar to the one that you get in flat space. So let's have it here on a cleaner slide. And in particular, it's a very, very degenerate spectrum that you get in this way. Because if the total number of oscillators, the total mode numbers, the sum is very large, you can obtain many, many states that have the same energy. It's also much simpler than, of course, ADS5 process 5. If you think of the Konishi spectrum, for instance, that's much harder to express. You cannot write it in closed form, but you have to write it in some sort of approximation order by order with very complicated coefficients. I didn't say everything. There are other sectors of the spectrum. There is a long string continuous spectrum, but by and large, is what I want to have in mind for the spectrum of this very special point, which are the Zumino-Witten models on the worksheet. Okay. Then what you can do is that you can deform continuously away from these Zumino-Witten models. This was done in described in many places, but I like particularly this paper by Ola Paulson, Stacks, and Bogdan Stefanski, where they explain it very nicely. So that tells you that you have a family of backgrounds that stems from any of these choices of K, continuous family. What happens is that now you also have a Ramon 3-4 flux. You can do more complicated things than this, but they are all equivalent essentially to introducing this 3-4 flux, this Ramon 3-4 flux. And now the tension changes because essentially the tension is a little bit larger now. You have to change a little bit the balance between RR and NS. And the cleanest way to think about it is this formula here in the bottom right, and to say that you have one parameter, which is the K that we had before, is the number of NS5 branes is quantized. And then another parameter, which is this H, and this H basically is whatever is in front this 3-form flux, and it tells you how much you have switched on the Ramon flux. And this is a continuous parameter. Yes.
Why wouldn't that just be subject to quantization rule?
Because I am in perturbative string theory, and a bit like in ADS5, this thing is some combination of a number of 5 branes and the string coupling, which goes to 0. So that this parameter is finite. You can also see it as starting from this geometry and turning on some axiom in the background, and that's a continuous thing that you can do. It's really a modulus.
To impose direct quantization on one integral with F3 or something.
So,
sorry, let me not interrupt.
Okay, we can discuss, but the bottom line is that it is a continuous parameter. Maybe it's improper to call it flux because the flux itself is quantized, but this is if you want the normalization of this contribution, and the same thing as in ADS5. So this is your string tension. Good. What do we know about these backgrounds? Well, we know that qualitatively we expect all these degeneracy that I described to be lifted by the introduction of this H. And we know that it's in principle possible, but in practice quite hard to compute how this lifting goes in the RNS formalism. So in principle, you could start from the SNS point and treat this parameter as small, and there's a paper where this was done to some extent, but
They were using Springfield theory. They weren't-
yes.
I wouldn't call it that.
I didn't, because I wanted to distinguish it to yet another approach, which is this hybrid approach, but yeah, okay, so if you want, it's worksheet CFD if you want, right? That's
No, but it's not, because it's Springfield theory. It's off shelf.
okay. Okay, point taken. So this can be done, or it can be tried, but you don't get very far, or at least so far people have not gotten very far. And the last comment is that there is actually a completely different family, which is not related to starting from this SNS story at all. And this comes from the D1D5 system. You only have Ramon background, you don't have any B field, and it's the one that is most similar to ADS5. And this presumably is as hard to study by RNS or worksheet techniques as ADS5 would be. Good. So what do you do? Well, hopefully you do integrability. And in fact, it turns out that for any H and K, the classical action that you get is integrable in the same sense as the ADS5 is. And this was done by Kostia and Alessandra Cagnazzo. And then you can hope to run the machinery that works so well for ADS5. And here I'm mentioning in particular the string approach, because notice that I've not been talking about duals at all. In ADS5, of course, it was very nice that you could also look at anyone. And now the idea is that you run this machinery and you get a spectrum for any K and H somehow. And let's see how this goes. Some of these will be very familiar to people that are familiar with the ADS5 story, but there are some differences too. So what do we do also in ADS5 and also, for instance, in Stipiler-Stoke? The idea is that we fix some light cone gauge and we study the gauge fixed theory. The light cone gauge is not terribly important what it is, but it corresponds to this tiny ADS and some equator on the sphere. And the bottom line is that it turns out that in this gauge, the Hamiltonian of your two-dimensional model, which will be your integrable model, is precisely this E minus J that I introduced before. Sometimes it's convenient to distinguish this total Hamiltonian as the part without the tildes plus the part with the tildes. That's just notation. The other thing that happens is that you lose the parametrization invariance, and the size of your string is related to the total R charge or angular momentum on the S3 of your classical string, classically, and then of your quantum string. Okay. So let's look a bit more closely at symmetries, and the total symmetry algebra is called PSU1,1/2, is smaller than the one that you get in ADS5, but it's very simpler. It's very similar. So it has SU1,1, so SL2R as the bosonic part, and another SU2SL symmetry, and 8 supercharges. And again, it comes in 2 copies like everything. Each of these copies has a BPS bound, which tells you that precisely this combination L minus J for unitary representations is greater or equal than 0, and it is 0 precisely in BPS states. So conveniently, the Hamiltonian that we cooked up is actually positive semi-definite and is 0 only on BPS state. Okay, then you work out the symmetries of this background, and indeed they fit into this algebra. And again, there are 8 G's and 8 G tildes, and they have 3 indices. Each of them can take 2 values, so yeah, the 3 is 8. This one at the bottom is the SL2 index, then you have an SU2 index of the R symmetry, and then there is this A, which is common, which is some other SU2, which is basically an automorphism of this whole algebra, but not terribly important. Then you fix the gauge, and in the gauge, your Hamiltonian was this H, and you can immediately see that not all of these superchargers commute with this H. H was L minus J, roughly speaking, right? So you need to have good, to pick, if you pick the M index, you have to pick a alpha consequently so that the L minus J of this charge is 0, or rather, this charge has to be the same value, same eigenvalue under L that is under J. So in this notation, which is slightly confusing, the good ones are basically alpha of the G's with plus here and minus here, and A can be anything, and alpha of the G tilde. So these are your supersymmetry and superconformal symmetry generators that survive. And you look at what algebra they form, and essentially G plus here acts, let's say, as a raising operator and G minus as a lowering operator, and their anticommutator gives you exactly H. Same thing for G tilde is exactly the same picture. If you do a semi-classical analysis, what you find out is that actually, somewhat unexpectedly, you find a central extension between the G's and the G tildes. Originally, they didn't speak to each other, but after gauge fixing, they do. That's, of course, not surprising, and in fact, it's a feature if you think of IDS5. It's the same central extension that Niklas and Aryutunov, Frolov, and Zanoklar and Plevka found in IDS5 process 5/n equal to 3 on this. So these charges here, the first time here I wrote them with all these indices because you see, even if they're called C, which stands for central, meaning that they commute with all these guys. They commute with G plus minus, they commute with H tilde, and so on. They do carry some R charge. They carry R charge under the left and under the right, and they carry some SL2 charge, right? It's just that it's a particular combination that is annihilated by this H. But it would not be annihilated by, let's say, L0 or L0 or just J left, or even J left minus J left plus J right. Okay, because it's a bit of a heavy notation, usually people abolish all these indices and they just call them C and C Decker because they are clearly conjugate to each other for unit representations. But it's important to keep in mind that they are central with respect to this model algebra, but they are charged under other stuff of the original PSU1,1/2. Okay. And then you consider scattering states of these two-dimensional thing and the worship of the string. And you try to fix what is the action of this C, for instance, on this scattering state. And again, semi-classically, you find the answer, and it has a particular form. And this form, first of all, is proportional to this H. So if you are in the NS-NS backgrounds, it's not there. There is no central extension whatsoever. That's the first important message. The second thing is that, like in ADS5, it depends on the total momentum, and it has the property that, in fact, this expression vanishes if the total momentum is 0, mod 2 pi. And that's good because for a physical state, which satisfies the level matching condition, which is precisely this condition here, you wouldn't want to have a central extension of your algebra, exactly like in ADS5 again. So this all looks very nice. The other thing is that there is a shortening condition for the representation under which this worksheet excitation transform, which relates H tilde and C dagger and C. And out of the shortening condition, you can solve it now that you know what C tilde is, and you also know what H minus H tilde is, and you can find the dispersion relation of the models. By the way, one thing that you immediately see is that if you are in this NS-NS model, what is model without Raman flux, this is the Mirovitte model essentially. So you don't have this H, you don't have this C. This condition tells you that either H is 0 or H tilde is 0. So your excitations have to be chiral, even in light gauge, which is not something that you would have here. So without further ado, I think probably the most beautiful formula of all this story, because it contains all the physics of it, I think, but it's still manageable, unlike the S matrix and other more complicated objects, is the dispersion relation of a single excitation on the worksheet of the string. And this formula is exact, quote unquote, meaning that it's fixed by symmetry, up to figuring out what is the physical interpretation of this parameter H, which we know what it is at strong tension of the string, but you have to figure out the weak tension of the strings, like in a BJM, for people that are familiar with the story. So dispersion relation depends on K and H. It also depends on the new parameter, which is called mu, and labels different representation in which this particle can transform. Mu goes from 0 up to K minus 1, roughly speaking. And it has a part which looks a bit relativistic, first one in the bracket, and the part that looks more like the dispersion of a lattice model. So let's take the two extreme limits. You drop the part with the H, you're back in this Mirovitte model, and indeed you have a the dispersion relation of relativistic massless particles, well, in a constant magnetic field to be precise. But roughly speaking, these are particles that move either left to right or right to left at the speed of light, and the speed of light is k over 2 pi. The other extreme is that you drop the k, and then you get the dispersion relation that looks very much like the one of ADS5 process 5, with one important disclaimer. In ADS5 process 5, this number here, which would sit where mu is, was an integer that went 1, 2, 3, 4, 5. Now mu can be in Z, and in particular, it can be 0. So in particular, this dispersion relation can have no mascot. This is related to the fact that you have this T4 in the game, so you have flat directions, and therefore you expect to have some gapless excitations from there. Very good. This dispersion relation has all sorts of nice properties that were studied starting here, and then the study was continued or picked up several years later by Bogdan Stefanski, Olaf, also Sachs, myself, Davide, and Sergei Frolov. But for instance, one intriguing one is some sort of periodicity, just to mention it. It's a curiosity, it's not important for the rest of the talk, but you see, this part here is clearly periodic, right? If you shift p by 2 pi. This part, sort of, if you shift p by 2 pi and you shift mu by k, you go back to the same thing, sort of. And k is precisely quantized in the right way, all these things are integers, so there is some very nice structure that then finds its way in more complicated objects like the S matrix and the dressing factors. Okay, the S matrix you pretty much fix by just asking that the symmetries are realized in a nice way on scattering states, up to the dressing factor that you fix by banging a red on the table for 2 years. And once you've done that sufficiently hard, you are ready to compute the spectrum of the model. And a cartoon, which will offend all the integrability experts, is that you put this model in the box, you say that now the momentum should be quantized by some sort of beta equation. The spectrum of the momentum will be quantized in some integers, 2 pi over L, 2 pi mu over L, mu is some integer, L is the volume, which have to do with some R charge, plus corrections that come from interactions, and in fact there are many more corrections that come to the fact that you have to honestly do something like the thermodynamic meta-ansatz or the quantum spectral curve, which I'm not going to explain. But the idea is that you have a discrete spectrum, you plug it into the energy, and you get your energy spectrum. And again, the real answer is TBA or quantum spectral curve. Results. Well, first thing, you can try to go back to this pure SNS background, like a madman, studied in Lightcom gauge by completely messing up all the symmetries, do the TBA, and you find back exactly the simple Belsomino-Witter spectrum. So that works, that checks out, that's nice. Pure Ramon-Ramon backgrounds, that requires substantially more work. So this would be k equals to 0, but you have this h. And there are, roughly speaking, 2 proposals on the market. One is the quantum spectral curve, which came out first. And this works very nicely, especially for the massive sector. And immediately the people that were working here in a series of papers were able to make predictions for excitation of massive states that only involve massive excitation. The TBA works in principle for everything, but the numerical study that we did was specific to the massless sector, and I will explain why later in the talk. And one question that is outstanding is whether these 2 descriptions agree, because basically they produce results in different corners of the story, and there is no mathematical proof that they are related to each other. So this is some outstanding question, but thanks to some new development, maybe we are not so far to checking whether they agree. Hopefully they do. Even more recent development is this more complicated case where everything is turned on. And now it took a while to find out how these dressing factors are made. They have a pretty involved structure, which I've never seen in any other integrable model. The mirror theory, for people that know what it is also a bit peculiar because it's non-unitarity theory, but you can work with it. And in the end, very recently, with Sergei and Davide, we formulated some mirror TBA equations. So in principle, we have all the tools to study the spectrum. So this was just a couple of months ago, but we have not gone through the pain of solving it numerically yet. So we don't have a prediction yet here. Okay. Before going too much into the rest of the story, I want to spend some time on one particularly simple and interesting corner of this duality, which is the weak tension limit. So if we were doing ADS5 process 5, this would be small Toft coupling ion beads. You would expect that this should be something nice, something simple. And here we have to understand what we mean by weak tension, because the tension is sourced both by the parameter k, which was integer, and by the parameter h, which was continuous. So there are at least two ideas that you can have to go at small tension. The most drastic is that you say k is 0, h is very small, and that's a bit like what you have in an equal form, where you just say there is a Toft coupling and it's very small, and they expand around 0 coupling. The other thing, which is known as tensionless limit for historical reason in the literature, is when you actually put k equal to 1, not 0, and then you expand in h being very small. And the reason why this limit is interesting is that it's one of the cases where we know very well and what the dual CFT is when k is 1 and h is very, very small, and it's related to a symmetric product orbifold CFT, which people can study quite exactly. So let's talk about these limits, unless there are questions. And I will start from the k equal to 1 case, which is, I think, the best understood. So we have the symmetric product orbifold CFT of T4 that arises when h is precisely 0. And the idea is that you take a theory of free bosons, a CFT of free bosons and fermions, supersymmetric. You take n copies and you mod out by the action of the symmetric group Sn. And in fact, what we are interested in is an n to infinity limit of this story. So in this theory, we have cycles, and you write down your states as product over cycles. But if you're at large n, it's enough to understand the single cycle sector of this theory, exactly like in an equal 4. If you're at large n, you can be content to study the single trace. So single cycle is like single trace here. And roughly speaking, if you are in this theory without any deformation and you're just interested in the spectrum, it's actually quite simple to work it out. Because what happens is that each cycle has a reference VPS state, which would have 0 energy under this H, which is A minus J. And then you can create excitation by acting with bosons and fermions of this free orbifold. And the only thing is that because you're in a cycle of length L, your bosons and fermions, they're not integer moded, but they are moded in modes that are n over L, units of 1 over L. There is a physical state condition, which is eerily reminiscent of the level matching condition. It tells you that the total mode number in the left minus the total mode number in the right has to be 0, mod L. And you can compute the spectrum just by adding up all the mode numbers of the left oscillators and all the mode numbers of the right oscillators. Okay? That's it. That's the spectrum. It is, after all, pretty much a free theory. If we take this NS dispersion relation and we put k equal to 1, h equal to 0, omega is just 1 over 2 pi modulus of p. And then if we just declare, okay, maybe it is just a free theory, the modes are quantized in units of 2 pi mu over L, you plug it in here, you reproduce the same spectrum. So that's all fine, but of course, this theory, I mean, it's very interesting to study this as orbifold if you study complicated objects like several point correlation functions, 1 over n correction. But as far as the large n spectrum is, it's a pretty boring theory. And you want to do something a little bit more interesting. So you want to deform it, which should amount to turning on some h greater than 0. And this means making so that left supercharges and right supercharges don't anti-commute. And this can be done by introducing some deformation. In fact, it is understood what is the dual of turning on a monomon flux. And this is basically some particular marginal operator which happens to come from the L equal 2 sector of this orbifold. So there are BPS operators, there are many moduli in this theory, but the moduli of the orbifold and the moduli of the theory have been matched, and this particular one is the one related to, or that should be related to the Ramadan flux. And ideally, we would expect that there is some sort of expansion where taking a order by order deformation in lambda corresponding to some small h of lambda, something like this. So what we want is roughly to act on with the right moving operator, supercharge, sorry, on some state that only contains left excitations. You see, if this were in the undeformed theory, left and right guys would just commute. So I could just hit the vacuum with this supercharge and it would annihilate it. But somehow in what we expect from the representation theory is that if h is not 0, this should not be 0. In order to make sense of this, if you look more closely at the labels, you see that, for instance, this guy has an R charge which is related to L here in the vacuum. And then I act with the guy that is charged under the right R charge, this G tilde. So I increase the right R charge by half a unit. And in order to match the charges, because here I can only put excitations without a tilde, I've got to decrease the left R charge, but increase the R charge of the vacuum. So this is the length changing effect that you also have in ADS5 process 5. And it means that, strictly speaking, this action here is only defined if L is infinite. More precisely, it is nice. Should I pick up? So in Italy, we get a lot of spam calls, and I should have silenced my phone in a more efficient way, I suppose.
I like the way you looked angrily at the room.
Who's there? Who's there? Okay, back to us. So people that were asleep can reconnect. So this actually only makes sense if L goes to infinity. And as a result, you have to sort of work out what happens in this orbifold when L goes to infinity, N, which was the mode number, goes to infinity, so that this ratio N over L is fixed, and that would be related to the momentum of your excitation. Roughly speaking, that, for people that are familiar with CFT, means that you do a computation in first order perturbation theory, where on the one hand you have the state on which you would like to act, you have the supercharges, the supercharge on with which you act, G tilde, and this is the guy that it would spit out. But you also stick in the middle this deformation operator and you integrate over the whole space. There is a whole story on how you do this, but just to give you the bottom line, so this computation was actually attempted, at least for small n over L, a long time ago by Gava and Narain, and they found some central extension way before people started looking at this sort of thing in ADS5 process 5. But they were looking at PP wave, they were trying to match the story with k equal to 0 and k equal to 1, so it never really clicked completely for them, I would say. More recently, this was revisited by Gabriel Diego, Pacuma, and Nairns, and they did this computation. They got some algebra out of it, and they produced some S matrix. Initially, they were thinking that they found some new S matrix, but it turns out that if you match with the correct representation and you read a bit more carefully, you find, in a sense, what you would expect from integrability is just the expansion of this general structure that you have for any k and h when you put k equal 1 and h small, in fact, just h equal lambda. That's the trick. There are a couple of problems with this k equal 1 story that one has to be mindful of. So one is this dispersion relation here that now I wrote for k equal to 1. I wanted to have overlays, but I forgot. So let's just look at the first line, shall we? So you have this expression here, and you expand it at small h of lambda, which just tells you that you have p over 2 pi, that's the leading order, plus something that is of order lambda squared. As long as far as p is not 0. However, in this orbifold, if you just do a honest computation in the orbifold, forget about integrability, you just do conformal perturbation theory, there are infinitely many states which get corrected at order lambda. And it's not obvious at all that they are related to having p equal to 0 in this story. They just seem just a bunch of states that have this property. There are not many with respect to the whole number of states, but it's an infinite family. So could it be that in fact in this theory you have wrapping corrections that are more leading than the first correction that you would get naively from the energy, that basically come at order lambda as opposed to order lambda square. So wrapping is essentially not just as important as everything else, but more important than what you would expect by your asymptotic Bethe-Ansatz. It's not a very improbable proposition, because after all, you have a bunch of guys, you have a bunch of soft mode in this theory. The theory is very, very delicate. So one could imagine something like that happening, but it would be a very impressive test of the integrability story if one could reproduce this behavior and the numbers, of course. So in this paper, we actually, with Fabri and Torben, we actually work out a bunch of these numbers if people want to compare. The other thing is that in this paper, actually, the way that in which limit L to infinity was taken was not, in my opinion, quite right. So this seemed to work fine as long as one wanted to reproduce this algebra. But if you want to do something like compute, for instance, the perturbative S matrix, the dressing factor, all these things that are a little bit more delicate, it's not entirely obvious to me that the procedure that was used there could be generalized or that would work. So maybe one has to take another look at how to take this limit in a more rigorous way. So this is for k equal to 1. Let me talk about k equal to 0 now, which is in a sense even more tensionless and should be similar to n equal 4. So again, let's look at my favorite formula, the dispersion relation, which now has this periodic lattice structure. And remember, this mu here is the mass of whatever particle. And we expand it at small h. And that's an obvious thing. If h is equal to 0, so it's mu is equal to 0, the leading order is of order h, otherwise it's of order h squared. So at small tension, the leading corrections to this story come from states that are related to the T4. So that's quite interesting, because you see, in the k equal to 1 story, it so happened that the dual was a symmetric Raunfold of T4, and then in a sense the ADS3 cross S3 came through excitations on top of that, but you started from the T4 fields. Now you are at h equal to 0 and k equal to 0, and you find something very, very similar, that is the T4 modes that dominate at weak tension. So maybe you get excited, you think that could be the same thing, it's again the Raunfold of T4. Well, you can just check, because we have the Bethe-Ansatz, the TBA, and you can go and solve the TBA. So you take the whole TBA, you expand the TBA order by order in H. That's actually the honest way to find whether the correction comes from which modes, because the argument with the dispersion relation is a bit weak, to be honest. But even if you are very careful, you find that it is only the T4 modes. You get a very nice TBA of difference form with non-relativistic energy and momentum. And then you compare whatever you get from this TBA with the naive expectation, which should be something like the momentum is quantized in some fraction of an integer, and the energy is given by the dispersion relation, which in this case has this sign, plus corrections. So this is something that we could only do numerically. We don't know how to solve this TBA any better than that. And we did it for some states. For instance, here in the plot, you have two states of momentum P1 and P2 that are one of the opposite of each other. You need that for level matching. We chose some values of L. So here you have L equals 4, L equals 16. And what you find, the important things here are basically the red dots and the dashed line. What you find is that the dashed line is what you would have for a free theory with dispersion relation sine P over 2. And here you get some correction. It doesn't look like anything simple. It doesn't look like the orbifold of T4. That would have been just a straight line for these red dots, which it isn't. It looks like an interacting theory. If you start putting more and more excitations, the energy is not just additive. So this is, in a sense, the equivalent of one Luppian Mills. Should be something simple. In one Luppian Mills, we know that basically, if you look just at the sphere, is an XO6 nearest neighbor speed chain. Here is something that is described by some TBA. It's a quantum mechanical model with long-range modes, basically. and that spits out these numbers. So it's a very interesting question what it is. So this is the spectrum of what? Okay, let me conclude with some overview of what I told you. So in the NSNS case, I didn't really talk that much about it, but this is in a sense a very old story, very nicely understood. You have a Resomino-Witten model. You know the dual because you know what happens at k equal to 1. I should mention there is also a proposal for the dual at other values of k. It's a bit more complicated. That is a paper by Lawrence Eberhard of maybe 3 years ago. The tension is quantized. The spectrum is very simple. And if you are so inclined, you can also study by integrability, but everything can be understood very nicely by conformal filtering on the worksheet. On the opposite side, we have the pure Ramon case, very similar to IDS5. It's related to the D1, D5 system. You have essentially a Toft-like coupling, this H, which is a continuous parameter. The spectrum is complicated. For instance, in the quantum spectral curve paper, there's some numbers, some expansion, and it looks as nasty as Konishi, maybe even more complicated, something like that. But we don't know the dual, even if we know in principle how to deal with the spectrum. And the mixed flux is, of course, the hardest. It's a generic setup. You have H and K. At K equal to 1 and small h, you should get the dual from this perturbation, but in general, it's very hard to understand what to do. And the big news is that since a couple of months, we have TBA equations, so in principle, we can start spitting out numbers and comparing with things, checking proposals, and so on and so forth. Okay, that's all I wanted to tell you. Thank you very much for your time.
Do we have questions?
Did you say something with the K3 and S3 cross +1 kit?
So K3, I think that so the for integrability, not much has been done, but if K3 is an orbital of T4, I think things will go through quite easily. And if not, I think nobody has any idea of how to do it. For S3, S1, the thing is a little bit more nuanced because there is an S matrix. There is integrability, there is an S matrix. There is quantum integrability in the sense that this S matrix needs to pass several non-trivial checks and satisfy the Ambassador equation. But this step that I mentioned is very technically involved of finding the dressing factor, the prefactor that contains all the dynamics and that has non-trivial analytic properties, has not been done yet for S3, S1. As far as I'm aware, there are several colleagues that are working on doing the quantum spectral curve for S3, S1. I'm not completely sure, maybe some people in the room can comment, but there is a particularly simple case. So S3, S1, ADS3 cross S3 cross S3 cross S1 has these two spheres, and there is another free parameter, which is the relative radius. If the radius is precisely equal, then things are a bit simpler, and the algebraic description is given by an OSP type algebra, for which the quantum spectral curve could look a little bit similar to what we have in a BJM. The more general case, I think, is going to be substantially more complicated because you have this V2 alpha algebra, which is a little bit different. So there is work in progress on S3, S1, not so much on K3.
Dan?
You mentioned in passing, I think one of the main points of the agree Maldacena papers was the long string modes that are related to these S as a half plus IR continuous family of reps. Do you see those in the integrability in the TBA or in any of that? Are they still there, or are you ignoring that? So I think that the general consensus is that these long strings would only be there for the pure NSNS case, and it's because essentially ADS is a confining potential, and the B field makes it so that your strings can get all the way to infinity. Yeah. There is a work where using this Berkowitz-Witten approach, Eberhard and Ferreira checked that this long string continuum disappears even if you perturb infinitesimally away from the NSNS. So they're a very special feature, I think. And maybe even a bit of a misleading thing in a sense that, if you throw a dart, you will never see the long strings. You throw a dart in the parameter space. Yeah, but they're needed for like modularity of the CFT. Yes, I don't have an understanding of what will. Sorry, I think it's
maybe not quite.
Uh-huh.
I think that modularity, you need to have the things which I had on my slides, which were highest weight representation and spectrally flowed representation. Those are related by modular transformation. The long string continuum is modular invariant,
In
but
itself.
in and of itself.
I see.
Yeah, so here at some point at the very beginning, I had this thing and I was saying that these are highest weights, but I lied because you also have spectrally flowed representation. Those are needed by modularity. Those are captured by the TBA, no problem. You have a question? Yes?
You showed some results for the mirror TBA.
The amount case.
So how much of those results depend on the explicit form of aggressive phase?
They do quantitatively, of course, but qualitatively it doesn't look like. So this is work in progress. We are looking with, so there is a whole story about what precisely should be the dressing factor, and it has to do with the exchange relations of the model. This was with the original proposal. So this is taken from the old paper, if you wish. I don't think it changes. So we are redoing the computation, but it seems that it changes quantitatively, but not qualitatively.
There's no magic.
I would have, so the TBA becomes much simpler. For people that are experts, I will just say that the TBA is such that there is no, so there is a momentum carrying node, there is no kernel for this mode, and all the interactions come through coupling to auxiliary nodes. Roberto Tatteo had explained to me some model in which this happened, so this is something well known, but now it escaped me. So it's a simpler model, but the solution is still not straightforward.
Right, I don't see any further questions, so let's thank Alessandro again.